Okay, very good. Here we go. So thanks a lot, Pierre. Thank you for the invitation. So my name is Jean-Jacques Greffet. I'm working at the Laboratoire Fabry at Institute of Optics in Palaiseau. So I will be discussing how it is possible to control both absorption and emission with metasurfaces. Actually, I'm going to discuss in detail what metasurfaces are in the second part of the talk. In the first part, I'm going to discuss a few basic ideas regarding how to control absorption and therefore emission using Kirchhoff law, as was discussed just a few minutes ago. Using roughness, relative cooling, that's the exact opposite of what we've been discussing before, which is absorption. So it's easy. You just do exactly the opposite. And then I will be discussing relative heat transfer at the nanoscale, which is a totally different world from what we've heard today. We will see how we do in time. In order to discuss this concept, and particularly when I go to the nanoscale, it's impossible to do nanoscience without merging all different topics like physics, chemistry, materials, quantum optics, and so on. So please interrupt me at any time. I'll be trying to give you different perspectives, different ideas, and mostly focus on physical mechanism. I don't know exactly what's your background, so please just interrupt me at any time, and I'll try to give other perspective. It's the one I'm offering is not fitting what you would like to hear. Okay. So a few ideas regarding the general context of this series of seminars here. Surface engineering in terms of sustainable development. One obvious thing is photovoltaics. That's what we heard just before. When you think about energy, first thing you think is transformation of energy from one form to the other. And of course, you need to improve all those things. You can try to spend less energy. That's the efficiency of the sources that you are using. So this is about collecting energy. This is about transforming energy. One of the things I'm briefly going to touch is how could you recover generate electricity out of sources of heat which are at low temperature, and usually this is wasted energy. So how is it possible to try to recover that? In the near field, we'll see that there are a few ways of managing the heat transfer. But one of that's the last one, but it's certainly not the least one. One of you probably know that most of the energy consumption has to do with fabricating materials. So one of the best answers about saving energy and saving carbon is to try to reduce the amount of volume, weight of material that we produce. So we'll be discussing, is it possible to reduce the optical systems by texturing the surfaces? So, and that's where metasurfaces are involved. That's the second part of the talk after the break. Is it possible to reduce a bulky optical system and make everything in a thin plane, a metasurface, which of course would use tremendously less material? Okay, that's for the general ideas. So let me briefly go to basics. That's what I'm going to discuss. Essentially, spontaneous emission. This is incandescence. Most of what I will be discussing mostly about incandescence, thermal emission. And I want to emphasize right now that everything I'm going to say can be extended, and that's what I'm going to do if time permits in the last part of the second talk. This can be extended to electroluminescence and photoluminescence. So I'm going to try to convince you that by texturing interfaces, it is possible to do a lot about controlling spontaneous emission. All the examples I'm going to give in the first part of the talk is about thermal emission, incandescence, but all that strategies can be used for photoluminescence and electroluminescence, meaning LEDs. And all the strategies I'm going to use can be used to extract more light from LEDs and so on. And there is a fundamental reason for that that I want to explain. Okay, back to basics. Key idea, key concepts here is radiance or specific intensity, luminance in French. So this is an area. And this is a concept that's coming from mechanical engineering or optical engineering or radiometry, you name it. That's the emitted power per unit area, per unit solid angle in a given frequency interval. So that's essentially the optical étendue. And that's this coefficient, this function here, which is a function of polarization, frequency, temperature, direction. This is the specific intensity or radiance emitted if we're talking about emitted by a surface. And as we heard before, this is given by the black body specific intensity times the emissivity. So here the point is that if you can control emissivity, you can control everything about that, because this one is universal. That's what Kirchhoff demonstrated in 1860, well before the concept of Planck's function was known. He found that there must be something that turns out to be Planck's function, which is universal, depends on temperature and on frequency, and nothing else. So all the peculiarities that you want to control, they are in emissivity. So if you can engineer emissivity, you can engineer everything about emission. Second point, so this is a purely phenomenological theory, what I've just described. You have this theorem that tells you that there is some upper bound, which is Planck's function, and then the rest, it's a number that you measure. You don't have a clue where it's coming from. This is another picture that I want to propose to understand thermal emission. And so this is the picture that we see in physics classes about light emission. You have excited electronic states, if we are talking visible, lower electronic states, and you have an electron-hole recombination, or call it as you like, a radiative relaxation path from one state to the other one. And of course, you know that the population, according to Boltzmann distribution, the population of a highly excited state here, if the energy difference between these two states is h bar omega, then the population here goes like, the ratio of population goes like this exponential. So this exponential here in Planck's function is nothing but the fact that to emit at omega, you need to have an electron in an excited state, which recombines, and the probability of having indeed an excited state goes like that. So that's why it depends on temperature. So that immediately tells you, given a temperature that you have, what are the frequencies you may find in your thermal emission. Okay, that it's a direct consequence of Boltzmann distribution. Okay, third picture. This is I'm going to need a lot this one. When you look at thermal emission, so I'm emitting my body is at 300 Kelvin, so I'm emitting at 10 micron right now. From the classic electrical engineering picture, so when you go to classes or when you teach, you give this picture of electron-hole recombination. There is another picture in the electrodynamics class that you give, which is the antenna. If you have an oscillating dipole, a charge oscillating, it does radiate. It's a completely different picture, but we tell to all the students, yes, it's different, but it's the same. That both we call it radiation and emission of light. So in this picture, you have a current, and usually if it's an antenna, you are applying a perfectly deterministic current at a given frequency. In your cell phone, it's typically 1 gigahertz. You have electrons oscillating in a wire, and that emits radiation. Now, thermal emission can be described with the same point of view. What I'm writing here is just according to the linearity of Maxwell's equation, any electric field is proportional to the current density. So if you have a current at frequency omega, then you have an electric field at frequency of omega. That's just linearity of Maxwell's equation. In the middle, there is an object. It's linear, so there must be some object, which is a matrix. It's called Green's tensor. Now, on average, if the motion here of the currents, now there is no antenna, there is no applied voltage. I just have my body. And in my body, I am emitting radiation. So where is the current from? The current is from the fact that there are charges in my body that are randomly moving because I'm not at 0 Kelvin, I'm at 300 Kelvin. So these charges are moving randomly. Those could be electrons or it could be ions. There are plenty of ions in my body. They are charged, they are moving all the time. So it's a random movement, so they emit light. On average, this is 0. So on average, this is 0. But when you look at the power emitted, you know that you have to compute the Poynting vector, which is a quadratic quantity. So you need to take the square of this guy. So you have J times J. So you have this correlation function. So that's the source. So this is the fundamental quantity that you need to know if you want to understand thermal emission from a radiation antenna point of view. Okay? Now, there is a statistical physics theorem, which is called fluctuation dissipation theorem, that tells you that this correlation function, power spectral density technically, is essentially proportional to the imaginary part of the body, of the material. So this, and this Planck's function. So this is where Planck's function is coming, and this is the idea that if you can absorb, you can emit. This is the idea of Kirchhoff law. It's embedded in there. And the connection with the previous point of view is that if you have two states, they can either absorb or emit. So they are in there. The previous picture is in there. Okay, so there are the three pictures that I'm going to use to discuss thermal emission, and mostly this one, because with that one, I can do calculations, exact calculation. If I have a metasurface, I know exactly what a dipole in a metasurface will emit and how it will change modified by the metasurface. Okay, with that, what we know about incandescence is that, so incandescence, this is typically what I've shown you here. Oops. If you have a fire, it's the same. If you have any hot body, it's the same. The infrared radiation I'm emitting is the same. This is isotropic. The spectrum is broad. It's Planck's spectrum, essentially. This is unpolarized, mostly. You cannot turn on and off this to do what you do with a laser to transmit information and modulate the intensity. If you turn off, you wait for a few seconds until it cools down, and maybe more than that. So the rate of transformation is very slow. So those are all these well-known properties of incandescent sources. Isotropic, wide spectrum, and polarized, low modulation rate, low efficiency. You know that incandescent light bulbs have been banned from the European market because efficiency is low. And of course, low brightness. Brightness is how many photons you have in a given mode. The brightness of thermal emission is very low. So the question now is, well, that's the situation since Edison. Is there a fundamental reason for that? And regarding brightness, there is a fundamental reason, because the brightness, number of photons per mode, is given by the Bose-Einstein distribution. And indeed, in the infrared and the visible, unless you are at a few thousand kelvins, this is a very small number. All the rest, there is nothing in physics that prevents you to change that. Nothing. So that's what I'm going to do point by point. I'm going to check all those, and I'm going to show you that you can do that. And if you can do that, actually you are controlling spontaneous emission, and you can do that also for LEDs and so on. And that means that potential, and just by structuring the surfaces. And that means that you can design metasurfaces that have many functions. Okay, so that's the program. So let me go back to Kirchhoff law. We heard about Kirchhoff law. I would like to give you a hint on where this is coming from. The first naive answer is from the paper by Kirchhoff, which you can find on internet, and I recommend an English translation, and I recommend to take a look. It's very nice. But when you look at that, you have essentially energy budgets conservations plus at some point, you need to invoke reciprocity, Helmholtz reciprocity theorem. Helmholtz reciprocity is an electromagnetic property that tells you that if you have a force here and the detector there, you exchange them in this room, in a complex environment, then you get the same thing. You can exchange source and detector. It sounds a little bit like time reversal. It's not time reversal, but it's this idea of exchanging. If you have this reciprocity theorem, you can prove that. Now, let me emphasize that this is an amazing property, because on the left side, this emissivity is really something that you learn in thermodynamics class. It depends on temperature. So this is a thermodynamic quantity. And on the right side, you have alpha. Alpha is the absorptivity. So you have a material, and if you want to compute absorptivity, you send a plane wave on this material, and you can compute how much power is absorbed. So this is, you send a plane wave, this is fully coherent. So on the right side, you have coherent optics, on the left side, you have thermodynamics, and you have this equality. So this is not trivial at all. This is amazing. It's a magical thing that enables you to do coherent calculations. And I emphasize that you can design interferences and then you control something which is from the world of thermodynamics, incoherent energy. Okay, so this is far from trivial. It's true, it works. It always works. So where it's coming from? So this is a direct optical proof. This is you recognize a sheet of paper, white, with black paint. This is a visible picture. And then if you look at the emission, here you have what it is with an infrared camera. I'm cheating on you because Kirchhoff law is for a given frequency. On the right, it's visible. On the left, it's infrared. So I'm not proving anything. It turns out that, yes, white paper is also white in infrared, and black paint is also black in the infrared. So I'm not cheating really, but strictly speaking, I'm checking. Okay, so that's Kirchhoff law. I would like to give you a hint of where this is coming from. And it has to do with the topic of this series of lectures. It's about surface properties. So apart from the fact that it's a magical thing, let's look at what is absorptivity. You shine a plane wave on a body. Let's assume that this body is thick enough so that there is no transmission. So either the energy is reflected or it's transmitted by the interface. And then the thickness here is, this is absorbing, and the thickness is large enough so that there is no exit here. So the transmission I'm talking about here is the transmission of this interface, not the transmission of the slab, as before. Okay? So you see that everything that is transmitted at the interface, the fate of all the photons is to be absorbed at some point. So transmission by the interface is the very same thing as absorptivity. Okay? Good. Now, second thing, what is emission? Well, as I told you, we have, I'm using the picture of charges which are moving randomly in the body. Because of temperature, which is non-zero. So all these charges are radiating. So each volume element in the body has a random dipole moment because all the charges in the matter are moving randomly. And they are emitting. They are emitting photons. And even though the material is absorbing, and we tend to think, no, there is no light inside an absorbing medium. Yes, there is light inside an absorbing medium. The photons are emitting, and they emit photons. And those photons don't go very far if the medium is lossy, but there are photons. And there must be photons. Everything is in equilibrium. You are saying it's temperature T. As soon as you say it is temperature T, you are saying this is in quasi-local thermodynamic equilibrium. So you have phonons, you have electrons, you have photons, all that stuff is in equilibrium. So there are photons inside any absorbing material at temperature T. These photons, they are emitted right here close to the surface. They may be reabsorbed. Some of them will make it to the interface. And if they make it to the interface, they are either reflected or transmitted. Once they are transmitted, they are out there in the vacuum, and you call them emitted. So you see that emissivity is nothing but the transmission from medium 2 inside to medium 1. So emissivity is transmission of the interface from 2 to 1, and absorptivity is transmission of the interface from 1 to 2. According to reciprocity, they are equal. So that's Kirchhoff law in a nutshell. Okay. So this is what I'm trying to say here is that this is a fundamental property that is valid always. It's coming from fundamental principles. Now I'd like to discuss how we can engineer this absorptivity and therefore this emissivity playing with roughness. And this is very often what's been done for photovoltaic cells to try to increase the absorption by these interfaces. So the very simple ideas I would like to discuss first here is the different absorption regimes. So I take as a model for a rough surface, I take a grating with this sawtooth profile. It's characterized by the height h and the period d. In the geometrical optics regime, the wavelength must be very small as compared to all the parameters. Otherwise, the concept of geometrical optics is not valid. So if I think in terms of geometrical optics, I can use the concept of ray. And in terms of ray, this is what happens. I have a ray. It obeys reflection rules. So you see that as compared to a flat surface where there would be only one reflection event, so one attempt to be transmitted, here I have two attempts to be absorbed, transmitted, and therefore absorbed. So you increase absorption. Because if you're not absorbed here, then you have a second chance to be absorbed. So you do increase absorption. I call this ray trapping. And you see that if you take this type of profile by increasing h, you increase the number of chances to be absorbed. So this is just ray trapping. That's the type of absorption that you may have in this geometrical optics regime. Now there is a completely different regime, which is homogenization, which is when the period d is much smaller than the wavelength. So, oops, sorry. So here the wavelength is much, much bigger than that. And therefore, you can assume that this grating is actually an effective medium with an effective index, just for the same reason that you are saying in the first place that your material is a homogeneous material, and you know this is not the case because it's made of atoms, and every 1 angstrom you have an atom, so it's certainly not homogeneous, but because the period, which is angstroms, is much smaller than the wavelength, you can assume that it's homogeneous. Well, this is valid even though the structure goes all the way to lambda divided by 10, roughly speaking. In this regime, you see that if you look at the average along a line here, you have mostly vacuum and from time to time a little bit of material. If you make a cut here, you have mostly material and a little bit of vacuum. So if you average, and you need to see how you average, depending on the polarization, you either average epsilon or 1 over epsilon. Then you end up with this picture. So this, in the homogenization regime, so if the period is much smaller than the wavelength, then it's equivalent to that. Now, if you have such an index gradient, then you reduce the reflectivity. Why is that? Well, in the first place, for a given interface separating two medium, vacuum, and a medium with refractive index n, you see that the reflectivity is proportional to the contrast. Now, if you introduce an index, you have a continuous variation. So the local contrast, well, this is just because I was lazy and I made only 4. But if you make a continuous gradient, then you see that the local contrast tends to 0. So that's why when you have a gradient of index, you can suppress reflection. You can actually optimize the profile of the index to make sure that you totally suppress. And that's worked very well. And optimizing the surface profile amounts to optimize the shape of this grating, and it can be done. This is a broad spectrum absorption. It's something that is not very depending on the wavelength. So you make good absorbers and broad, with a broad spectrum of absorption. Okay, so those are two regimes, the ray optics, the homogenization. There are limit regimes. So in the middle, we have the resonance. So this is just an example of that you've seen that. This is it's called anechoic chambers. When you want to do tests for microwaves, you use this one. Here in this room, you have holes here. These holes are designed to absorb just with this mechanism. And it's the same in optics, in acoustics. And if you go to any concert hall, you will see this kind of structures which are absorbing. And whether you are in homogenization or ray optics, I leave it to you to compute. You have to figure out what's the wavelength in optics, 300 meters per second velocity. If you are at 1 kilohertz, you have 30 centimeters wavelengths. Then in the middle, so you have this so-called resonance regime. And these are, what I'm plotting here is in dashed line, the ray tracing calculation, so geometrical optics calculation. We compute the absorption using geometrical optics. Plain line is a rigorous solution of Maxwell's equation. So that's the reference. This is valid everywhere. You see that indeed for large periods D, they agree. So ray optics is, as you would expect, is valid. And here what we learn is how much larger than the wavelengths you need to be allowed to use geometrical optics. And surprisingly, it's only 2-3 wavelengths. So it's very rapidly quite good. I was very surprised when we did that. How small you need to be for homogenization to be valid. The green line here is the result valid for homogenization. So you see that it has to be smaller than 1/10 of a wavelength. 1/10 of a wavelength is more or less acceptable, not very good. If you are below 1/10 of a wavelength, it starts being quite reliable. And in the medium, you may have resonant effects. You have to solve fully Maxwell's equation. Okay, so this is a general knowledge about what's the effect on controlling absorption coming from interfaces effects. So now relative cooling. So we've seen that already. This is the atmosphere properties. So here you have different layers, the contribution of different gases. If you look at the overall, you see that the atmosphere will be, so what I'm plotting here is absorption or emissions, the same. So you see that it's transparent here between 8 and 13 microns. So this is why the infrared cameras that you can buy are operating between 8 and 12 actually. And there is another region here between 3 and 5. So those are the regions where the atmosphere is transparent. Of course, it's transparent in the visible also. So the idea to cool passively is to have a body which will not absorb the visible, so you may highly reflecting in the visible, and highly emissive. And beware, because you are receiving a lot of infrared from the atmosphere and from the sun. So you want to make it highly emissive in this region here, or this one, because if you increase the absorptivity, you don't increase the absorption because nothing is coming except from the sun. And on the other hand, those are infrared frequencies where at 300 kelvins, you can emit a lot. So you want to increase the emissivity at 300 Kelvin. Now there is an issue. It works because that's the visible and that's the infrared. You are emitting in infrared here at 300 Kelvin. So I've cut it when divided by the maximum divided by 2 orders of magnitude. So it's because of the spectral separation that you can play on these things, either increase as the previous application, or cool. Regarding cooling, there is still an issue because the sun here, it's at 6,000 Kelvin. So you see that the sun is still emitting much more than what you are emitting. So in terms of temperature, the specific intensity is coming from the sun is still well above the specific intensity that you are using to emit. So how is it possible that you manage to cool down, given that at 6,000 Kelvin, the sun is still sending you more light than what you are emitting? The answer is that the sun, you see it from a very small solid angle, and you are emitting in 2 pi to radians. And that makes a tremendous difference. So you are emitting much, much more than you are receiving. If you were surrounded by suns everywhere, it wouldn't work. So it's really because you are emitting in the vacuum. So what you have against you is not the sun. What you have against you is the cosmic background at 3 Kelvin. So you're on the safe side. Okay, so that's relative cooling. So now the next question, of course, it's the key issue is how you manage to have actually a device that works and has these properties. So one option is, let me shift, I think. So there are two possibilities that have been explored. One is to have PDMS, which is an organic material, a resist that emits in the infrared. And in order to make sure that you reflect the visible, you can use white paint. So this is oxide titanium particles. Another option is to use fibers, glass fibers, which will emit in the infrared and will scatter. They are essentially white. So they will reflect the visible very efficiently. Okay. So I'm doing in time. We have one more. I started half an hour ago, right? I've been talking for 35 minutes. Good, thank you. So I will try to spend 30 more minutes on this. Are there any questions at this point? No. Okay, so I'm moving to the near field. So what I'm going to discuss now is that there is this body here, which is at 300 Kelvin. And I'm going to ask the question, what's the energy per unit volume as I approach the surface? So here it's the energy per unit volume of the black body in vacuum. I'm asking the question, what's happening as I get closer and closer to the surface? I can compute that. I'm just going to show you what is the result when I do the calculation for silicon carbide here. It's going to look quite strange. Then I'll show you glass, amorphous glass. And then I'll give you a hint of what's going on and why it's so strange. So this is when you are at a distance here of 100 microns. The temperature, I'm doing the calculation looking at the emission by the body, and the body is at 300 Kelvin. So keep in mind, 300 Kelvin means that the peak of the black body spectrum is at 10 microns. So when the distance is 100 microns, I'm in the far field, I'm far away. Then 1 micron, this is smaller than the peak wavelength. This here is wavelength. This is energy density. So square of the electric field plus square of the magnetic field. That's what I'm talking about here. This is in hertz. In wavelengths, this peak is at 11 microns. So it's closer to 10 microns. This line where you see this thing. The way there a bit here, because this material, silicon carbide, has a negative refractive index, so it's highly reflecting. And this is the regions where you have phonons. So the material has a negative permittivity and the reflectivity is very large. It's so-called Reststrahlen region of the material. So because it's highly reflective, it doesn't absorb, doesn't emit. I'm plotting only what is emitted by the body. Now, when I look at the energy density close to the surface, there is a peak now where there used to be essentially nothing. Now I have a peak, and look at the scale. I have 15 times more energy than in the vacuum. And now when I go to 100 nanometers, which is quite small as compared to 10 micron, but if you're talking to someone doing atomic force microscopy, this is huge because your tip can be at a few nanometers from the surface or even touching, and you can control the distance within nanometers. 100 nanometers is really a lot. That's your black body. So it's a peak. So when I'm showing that, the question is, okay, but where are the photons which used to be there? Well, look at the scale. This is 1. This is 20,000. So these guys, the blue, they are still there. They are in the thickness of the line here. I should use a log plot, and then you would see them. So what I'm saying is that black body radiation is monochromatic, so temporally coherent in the near field. So what I'm saying is, if I'm an atom, that's the silicon carbide surface, as I'm approaching the wall here, I'm starting feeling the heat more and more and more. And the change is orders of magnitude. So there's nothing particular with silicon carbide. This is what happens with glass. You see, it's essentially the same story. It's broader. And the fact that it's broader is because glass is amorphous instead of being crystalline. So let me tell you what's happening with two different pictures. And it's very simple to understand where is this coming from. So the first picture is to look at what's glass. This is quartz. It's the crystalline form of silicon and oxygen. So you have the binding between the oxygen and the silicon. The oxygen, as always, is attracting negative charges. So the silicon has lost partially its electrons, so it has a positive charge. If you have, and of course you have a vibration frequency of this link, this covalent binding. When you have the oscillation here, it's oscillate at a particular frequency. And since the atoms are carrying charge, that's a dipole. So now I have a dipole, which is close to the interface and which is oscillating at a well-defined frequency. Now, if you come just on top of this dipole, then you will see the field in the near field. And you know that the electric field of a dipole goes like 1 over r cube. So as you approach in the near field at distances sub-wavelength, you have a divergence of the field like 1 over r cube, and therefore the intensity like 1 over r6. So that's the explanation of the fact that the spectrum is narrow. It's the peak that you see, just the vibration of this chemical bind. And the intensity is because when you are close to dipole, the field diverges as 1 over r cube. So that's what you see. A different way of explaining that is to introduce the concept of surface waves. So essentially what I'm going to do is repeat the same story, but in Fourier space. So instead of saying I have a dipole at a given point, now I analyze the currents in Fourier space. So there are electromagnetic modes in Fourier space, and one of them is a surface plasmon. So in a nutshell, a surface plasmon in a metal is something like that. You have surface charges, and you have oscillation. So this is positive charges, negative, positive, negative. So this is a surface charge density wave. It propagates along X. And you can look for the existence of such a solution. It has a dispersion relation. That's omega. That's the wave vector. This line here is omega equal k divided ck, where c is light velocity. And you have this behavior. This is a typical behavior of the dispersion relation of the surface plasmon. And here you have an asymptote, meaning that for that particular frequency, which is related to the plasma frequency. Then you have, for different Ks at the same frequency, plenty of modes. This is a mode. A mode is a wave that propagates along X. It decays exponentially along Z. So here in vacuum, above, or in the dielectric above the metal, it decays like that. This is the Z component of the wave vector. And because of the dispersion relation in vacuum, which is kx squared plus gamma squared equal epsilon omega squared over c squared, this gamma squared here, you see that when kx is very large, this is what's happening here. When large wave vectors, this kx is much larger than this. This is the kx. This is epsilon omega over c. So this is negative. So this gamma 1 is pure imaginary, and you have an exponential wave. So all those states are evanescent waves. They are all confined close to the surface. That's why you do not detect them if you are far away from the interface. They are surface waves, and they are all at the same frequency. So this is how you explain the frequency peak and why this energy exists at the interface and not somewhere else. It's the same story in Fourier space. Two different points of view to explain the same thing. Okay. Questions? Yes. Yes. Yes.
And so could it increase the spectrum you have in your emission field?
Yes, thank you. If you have you may have differences if you have anisotropic materials and crystalline, and yes, you need to take this into account. When you have amorphous glass, you average. And in practice, when you do measurements, you have a tip that has a given size, which is a few nanometers. So you are averaging over several nanometers, and this is thousands of atoms. So there is an average. You are not really detecting one single bind. Okay, for the sake of simplicity in the explanation, I was pointing out one chemical binding, but in practice, you are averaging over many of them.
And you can have different bonding state. I mean, you can have SEO, SESE, oxygen.
Yes, and you see all of them, and you have many peaks.
And you have many peaks.
Yes, you do have many peaks. Actually, in this case, let me show you. Oops, sorry, I'm not going the right direction. You see, you have many peaks here. Yes,
the peaks we have,
the different resonances of the glass. Actually, you can do spectroscopy of your material with that. You have all these peaks. And of course, you have the peaks provided that they are the so-called active infrared. So you see the optical phonons provided that they have a dipole moment. If they don't have dipole moment, you don't see them. So you don't see the acoustic phonons, for instance. You see the optical phonons.
Okay, thank you. And I'm not sure to have get when you say that you have the same thing in the overview, you say when you have a look on surface plasma and polariton, you have the view in the Fourier space. I'm not sure to see what do you mean.
Oh, so here I'm explaining the origin of the narrow spectral peak and the fact that the light is localized close to the interface on the basis of a dispersion relation. So this is omega and k. So this dispersion relation is the dispersion relation of a surface wave. This surface wave is a mode in Fourier space. Okay, it's characterized by k and omega. So I'm in Fourier space when I'm using modes. To represent the fields, either I locally look at the field at a given point, or I use the concept of modes. These modes are delocalized. Now, when I'm using the concept of dispersion relation, I recover the fact that it's monochromatic because I see that each point of the line is a state. And I have, at that particular frequency, I have one state, one state, one state, one state, plenty of states. So this is why I have a peak. Each state can host h bar omega, an excitation, okay? All the states have, they are harmonic oscillators. So all the states are hosting n+1/2 h bar omega energy. So since I have plenty of states at the same frequency, I have plenty of energy.
Okay.
How do I get from this picture the fact that the energy is large close to the surface but not away from the surface? From the fact that those states are surface waves. And how do I get the fact that as I get closer and closer and closer and closer, I get more and more and more energy? Because the state which is here has the decay length, which is like that. The larger kx, the smaller the decay length. So the larger I go there and the more confined are the evanescent waves. So I need to get closer and closer and closer to see them. So it's an explanation in terms of waves, modes. Okay. So I'm expanding the field in modes, right? I can have a field in direct space or expand in modes. Okay.
Thank you.
Some other questions? So here in the explanation, I've been focusing on surface plasmons. For silicon carbide, those are not plasmons, those are surface phonon polaritons, but the story is the same. We have the same structure of surface wave, and we have the same shape of the dispersion. The plasma frequency, here what we have is the longitudinal optical phonon frequency. Okay, this has been measured. So it's been predicted theoretically. So the measurements were done by Yannick de Wilde at PC, ESPCI. The lab is now called Institut Langevin. So to make the measurement, he's using a tip. So what I've just told you is that there is a lot of energy close to the surface, but not aware. So we're making an infrared picture. So this is how it works, the experiment. You have this surface. You do not shine light on the surface. It's emitting. We want to see the infrared emission of that surface. The photons are in there, but close to the interface only. So you take a tip, that's the tip, and you oscillate the tip in tapping mode. This is an atomic force microscope in tapping mode. So when the tip is here, it's illuminated by the near field. So it scatters light in the far field. And when you retract the tip, it's no longer illuminated. So you do not have any light in the far field. So by oscillating at 100 kilohertz, you emit light at 100 kilohertz. You use a lock-in, so you collect the scattered light with a Cassegrain objective. It's infrared. You send to a detector, and you use a lock-in amplifier. It's a very small signal, but it's doable. And with that, you can do an image of the sample. This is the sample. It's a piece of gold on silicon carbide. And you see these pictures. Those are images of the electromagnetic field. What you are seeing is these modes that I was just telling you. So here it's metal. So the modes are plasmons. So what we see are the plasmons. You see that there are fringes. The reason why there are fringes is that we see the modes. And this is very surprising because you would not expect modes for thermal emission because you assume usually the thermal emission is spatially incoherent. Now, why is it incoherent? Because for different wave vectors, different modes, the fringes do not have the same spacing. So when they all overlap, then you destroy the visibility of the interferences. And this is what happens in black body. In black body, you have all angles. So in a given plane, you have all possible fringes. And when you sum up all of them, you don't see anything. But here, we chose a width which is 10 micron here and 20 micron here. And we are looking at 10 micron. So we have very few modes in 10 micron. It's almost single mode. So we see the structure of the mode because there is one mode. So we see the coherence. It's coherent because we have a device that enables a few modes. So we do see the structure of the modes. So we really are imaging the local density of states, electromagnetic states in the structure by doing thermal imaging. And that's why we chose to change the widths. This is the narrow widths, this is the larger widths, and you see that the number of modes increases as you would expect. So the conclusion is that thermal radiation can be spatially coherent in the near field if you design properly your structure. And it can be temporally coherent because it's monochromatic. So both of them are possible. That experiment was in 2006. This one is in 2013. So it took 7 years to do the spectrum. We predicted that the signal was monochromatic. The first thing Yannick showed was that, yes, there are surface waves, we can measure them in the near field. But then to put that signal, which is extremely low, into a Fourier transform interferometer and get a signal and get the peak, it took 2 more PhD students. So that was published in 2013. And do I have the spectrum? Here is the spectrum. So you see that the spectrum increases as you'd expect as you increase the temperature, of course. And it's monochromatic. So there is not much to see because it's in the right place where you expect at the surface phonon polarity frequency. Okay, so now I change gear, and what I told you so far is that in the near field, there is plenty of light. Plenty meaning orders of magnitude more, 4 or 5 orders of magnitude more than away from the interface. So now the next idea is, okay, take a piece of material, just like the tip, bring it here close. It will feel that huge field. So it will absorb a lot more. So what about heat transfer? Well, this was known actually. Back to the 70s, people made measurements of the heat transfer in the microwave. So in the microwave, the wavelengths are 30 centimeters. So if you take planes separated by 5 centimeters, they are in the near field. So you do see these effects. And they've been measured. And the theory had been done by these guys. So everything was understood in the 70s. Actually, they did that when they were preparing the Apollo mission. And they look in detail how would operate these insulators, because Neil Armstrong was going to be called out there. So they were devising, they are sandwiched with multi-layers of relative screens. These are aluminum sheets, and you have a bunch of them. And that's why they started studying these things experimentally, carefully. And this is where they saw this strange behavior, and they understood everything at that point. Now, then later in the 90s, people started to try to do measurements in the infrared with that. And they couldn't measure the phenomenon. They couldn't measure because the heat transfer between metals is very small. Even though you enhance, on the first place, a metal is an insulator. It's highly reflecting. So this was inconclusive. So the topic was stop at that point. And when we came up with this new effect that if you have surface phonon polaritons, then you have a strong resonance because of this enhancement I just discussed. If you remove this peak, then indeed there is nothing. So for metals, you don't have much of enhancement. But if you take a crystal, so glass, and all these experiments had been done with metal so far. So if you do that with silicon carbide, then you would expect a huge heat transfer. So this is a calculation where you bring a particle, you put it close to the surface. You can work out this analytically. And you see 2 resonances. One is a surface phonon polariton resonance of the particle, and this one of the surface. And you predict a huge enhancement of the field. That's what you would expect, right? And if you take 2 planes, you have the same effect. So we applied this theory that was available, we just replaced the materials by silicon carbide, and we found that this that everybody learned in school is no longer valid in the near field, because you have additional channels. Regarding propagating photons, of course, it's still valid. But on top of that, you have now evanescent waves that can tunnel. This is just, it's exactly the same physics as total internal reflection. Frustrated total internal reflection is exactly the same physics. So you predict an 1/d square law when you do that. So here we are linearizing. If the difference of temperature is just delta T, you can linearize everything, and you can say that the flux is proportional to delta T. So assuming that these two temperatures are close enough, you can linearize. And then this coefficient H, which would be 1 here, when you are in the far field, then you see that if you go all the way to, say, 10 nanometers, which is reasonable, you see that you increase by 4 orders of magnitude the flux. So at 10 nanometers, you increase by 4 orders of magnitude. If you go to 100 nanometers, you increase by more than 100 the flux. So this is interesting, because 100 nanometers, this is doable. You can engineer planar surfaces separated by 100 nanometers. And now you can increase the heat transfer, the relative heat transfer, by 2 orders of magnitude. And keep in mind, it's monochromatic if you're using silicon carbide or some similar material. So something that increases the flux by 2 orders of magnitude and makes it monochromatic for thermophotovoltaics, this is interesting. Because what kills you, if you have in mind the Shockley-Kessler thermodynamic limit of efficiency for photovoltaics, what kills you is the fact that you are absorbing with a given band gap, but the incident photons are solar spectrum. So a few of them have the right frequency. Most of them has a lower frequency, you do not absorb them. Or they have a higher frequency, you lose the excess energy. And if you do the best you can do, you end up with 33% conversion efficiency. Before you start, you cannot make better than 33%. Unless you use several band gaps, which you can do. And if you are designing photovoltaic cells for a satellite, of course you do that, because money is not an issue when you are designing a source energy for a satellite, but for mass production, there is no way you would do that. Okay. So we did experiments to check that, this 1/d square. So the idea was to bring an object close to a plane. To bring a plane here, as in the calculation, would be a nightmare, because you need to make sure that it's parallel. It's extremely difficult. So that's why we use the sphere. It's a big sphere. So the distance here is going to be 100 nanometers. The radius is 40 microns. So it's not at all like in the picture. To measure the temperature, we use a cantilever here. This is an atomic force microscope. This is a glass fiber that is glued on this cantilever. And this cantilever is bimorph. It has a part of gold and a part of silicon nitride. And they have dilatation coefficients which are different, so that they bend if the temperature changes. So this is extremely sensitive, and it enables you to control the temperature. And you can make an extremely accurate position measurement of this cantilever using interferences. So this is an optical measurement. So this is the result. The line is the theory, and the dots here are the experiments for 2 different spheres. So this, you see that there is an excellent agreement with the old theory from Paul Dervanov and the measurements. And we were able at the time to go all the way to 60 nanometers. And since this first measurement, there have been many other experiments recently where people go below 10 nanometers, and it's still valid. So this is well documented now, these effects. This is just to give you an explanation on where are those modes coming from. So the first answer is, well, the field, if you, coming back to the two pictures I gave you in the beginning. The first picture is that the dipole field goes like 1 over r to the cube, so the intensity 1 over r to the 6. When you integrate over all the sources, it gives you a 1 over r cube back. The second explanation is in terms of modes. So if you think in terms of modes, I'm plotting the modes here. The label of the mode is the wave vector. So you have kx, ky. So those are surface waves. It would be plane waves in vacuum, but now we have surface waves. So you label your modes with the wave vector. The propagating modes are in vacuum. They all have kx squared plus ky squared smaller than omega over c. So these propagating modes, this is the usual mode that are transmitted or reflected. They are here. Now you have the modes which are totally internally reflected. They go all the way to n omega over c, where n is this medium, the refractive index of this medium. They are totally internally reflected, and they can tunnel. This is frustrated total internal reflection. So here you get a factor n additional. So you see that you have more modes. So in this mode picture, the reason why you have more energy is that you have more channels that are carrying energy. There are more modes. How do we count the mode? We say that the spacing in K space is 2 pi over L, where L is the size of the object. So you need to, the modes are the dots. You need to count how many dots you have inside the disk. That gives you how many modes you have on in channels. So you see that it goes like the area of a disk, so like the square of the radius. And finally, the key to what's going on here is that even though you don't have a mode, you have a pure evanescent wave with a very large K, it can still tunnel. And the cutoff distance, the larger Ka that can tunnel, is given by 1 over d. So this radius goes like 1 over d, so the number of dots goes like 1 over d squared. And this is how we can understand the 1 over d squared behavior. So it's universal, and this is where it's coming from. So that tells you where is this enhancement of the flux coming from. You have more modes, that's all. There is no secret, nothing magic. We can revisit this formula, having understood that the flux is proportional to the mode, number of modes. This sigma that we all saw, it's a cocktail of fundamental constants. It can be written this way: G naught times area divided by lambda square. That's the typical thermal wavelength. An area divided by a wavelength square is the number of modes. And this is exactly the conductance of a single mode. So if you have an optical fiber and you look at what's the heat transfer through a monomode optical fiber, you get this number. So that's the conductance of one channel. Each mode provides you this conductance. So those are concepts borrowed from mesoscopic physics that enables to analyze the transport. Okay, coming back to thermophotovoltaics. So the idea of photovoltaics is to have a photovoltaic cell here that transform the energy. Like I mentioned before, the fundamental thermodynamic limits called Shockley-Queisser limit is related to the mismatch between the spectrum of the source and the absorption spectrum. And the idea is to use a thermal source. If you use a thermal source that can emit at a single wavelength, then you solve the problem. And this is what is called thermophotovoltaics. So you use the sun, for instance, to increase the temperature of this guy, and you engineer the emissivity of this guy so that there is only one frequency where it emits. And that frequency matches the absorption of the cell. So that's a way to circumvent the issue of the thermodynamic limit. This is the concept of thermophotovoltaics. Of course, it works only if you make sure that this guy is perfectly insulating, so that all the absorbed energy is only emitted through radiation and nothing is lost by conduction, convection, and etc. So that's the concept of thermophotovoltaics. And now you can do near-field thermophotovoltaics, and the idea is that you take advantage of the fact that in the near field it's monochromatic. So that solves the problem of how you manage to have something which emits only at one frequency. And the second advantage of doing that is that the flux here, as compared to the flux that you have here, can be enhanced by 2 orders of magnitude, as we've seen. So the advantage of having a cell where the flux is enhanced by 2 orders of magnitude is that you may reduce the temperature. And that means that instead of having 6,000 Kelvin, you can have a low temperature source, and you can still extract electricity out of a low temperature source. That is typically what would happen with ovens used in the plants that produce glass. The walls are extremely hot and this energy is lost. So that's an example of a situation where it could be useful to have this kind of device. Now, of course, those are theoretical ideas. At the end of the day, you need to do a device, and people are working on that. It's not simple, it's not easy to do, but it's an interesting challenge. Okay, I think I'll stop at that point. What's the origin of this directivity? Like I said before, we have surface phonon polaritons propagating along the surface. They are excited thermally. But when you excite surface phonon polariton with a given wave vector, they can propagate over large distances. Typically, they can propagate over 10, 15 wavelengths. So it's 150 microns. So they will be scattered by this ridge, this ridge, this ridge, this ridge. It's the same surface wave. It has a given wave vector. You apply the rule, the grading law. This is your surface plasmon. Being diffracted, you end up with a given angle of direction here, which is the emission angle. So if you're looking at a given frequency, then according to the dispersion relation, you have a given wave vector. And according to grading law, you end up with a given emission angle. So that's the physical origin. So you see that where is the spatial coherence coming from? From the fact that each single incoherent source, which is here, could emit a photon, which does not very efficiently because you see that the emissivity is smaller than 10%, or it can excite a surface phonon polariton. If it excites a surface phonon polariton, this surface phonon polariton propagates over large distances, and this is what is producing spatial coherence over the surface. And it's been scattered in a well-defined angle. A different point will be emitting a plasmon, which is totally out of phase, but it will have exactly the same emission pattern. So that all these patterns will add, and we will end up with a nice directional emission. We can compute the correlation function directly above the surface, and this is what happens. So this is just to give you a further proof that this is related to the presence of a surface wave. So for Stanton in the visible, you see that there is no long range correlation. What I'm plotting here as a function of rho, which is the distance here, is the correlation of the function at a given point and at a given, so between 2 points, R1 and R2, they are along this line at a given distance above the plane. And they are separated by this distance rho. And you see that they can be correlated up to several wavelengths. A black body has a correlation length which is half a wavelength. So here you see that there is a long range correlation, and it's due to the existence of this surface wave, as explained before. If you go to tungsten in the visible, it's a metal, but it's a bad metal. There are no surface plasmons at this wavelength, and you see that there is no long range correlation. If you go to gold and silver, at this same wavelength, there are surface plasmons, and you see that there is a long-range correlation. In the infrared, silicon carbide at 11 micron has a surface phonon polariton. At 9 micron, there is no surface wave and there is no long-range correlation. So this is just to confirm that, yes, indeed, it's related to the existence of this surface wave, the existence of this surface spatial coherence. Now, this is again surface silicon carbide. Here we design a surface which is a two-dimensional surface. Previously, it was a one-dimensional grating. And we designed this surface in such a way that it would emit at normal incidence. This is the pattern that we have as a function of kx and ky. This is the emission. If we make a zoom here, you see that we have a peak. It's extremely narrow. And that's a detail of the measurement. You see that we have an angular width, which is about 1 degree. So this is approaching what you get with CO2 lasers, a 1 degree angular aperture in the infrared emission. So we can really have highly directional thermal sources using these tricks. So that's the first cross. Thermal emission, spontaneous emission is not spatially coherent, cannot be directional. It can be. And this is by designing properly the interface. Now we want to control the spectrum. So in order to control the spectrum, that's the basic idea. Starts by suppressing all emission. So there is no emission at all. There are two ways of doing that. Either you take silver, as was discussed before, it's a very good mirror, or gold. In the infrared, it's a very good mirror also. Or you take a dielectric material which is transparent. And then you add, here for instance on gold, you add a piece of glass. Glass has some losses in the infrared. It's a very thin layer, so it doesn't absorb much. And it's on top of a metal, so if you send light, the field interferes with the reflected field, so the field is almost zero, so it doesn't absorb much. But then you put a disk here, which produces a local resonance. And by designing the diameter of this disk, you can control the resonance frequency. In doing that, you enhance dramatically the field here. So even though there is not much glass, because you are introducing resonators, now the field is large and the absorption is significant. By having a periodic array of these guys, as before, you can have a huge absorptivity. And this absorptivity happens at a single frequency, which is the peak resonance of this resonator. That's the measurement in the far field. Same story here, the resonator is different. Here it's with silver, we have crosses, and you see that the authors here use two types of crosses with different sizes. So essentially, this guy here behaves as a Fabry-Perot resonators, so the frequency depends on the length. So here the length is longer, so the resonance is a bigger wavelength, smaller frequency. And you see that indeed, with a single type of crosses, you have only one peak for absorption, two peaks when you have two crosses. So you can design the absorption of your metasurface, and these peaks are wherever you want them to be. Look at the peak emission. It's close to 100%. So again, this is what I was telling you. If you think naively in terms of ray, you would say, okay, rays falling here will be absorbed at a given frequency. Those falling here will be absorbed at a different frequency. So with this naive geometrical optics argument, you would expect 50% absorption maximum at each frequency. And actually, you can have 100% absorption at both frequencies, because each resonator, each cross, has it's actually absorbing over an area much bigger, which is, again, the absorption cross-section, which is half a wavelength square. Now we move to the control of frequency and direction simultaneously. We want to design a metasurface that can be both directional and monochromatic. And in the design, that was a collaboration with the group of Xavier Letartre in Lyon. This sample was designed by in the group of Xavier Letartre. The idea was to have an emitter for CO2 detection. I'm sure you have a detector in your home, you have to detect CO2. it's operating on a battery, and I'm sure that many of these detectors in your homes are not working because you have not replaced the battery, because you have to do that every year or every 2 years. So here the goal was to have a system that would be operating with a single battery for 10 years. So you need to save energy. So that goes back to, is it possible to have an incandescent emitter which has a good efficiency? And I told you there is nothing in fundamental physics that prevents this to be the case. So that's what we did here. And actually we managed to have something that can be operated during 10 years. So let me first explain how it works, this metasurface. For the application, you want to emit in the forward direction. Everything that would be emitted on the side would be useless. The detector is up there. So you want to emit towards the detector. And to save energy, you don't want to emit in other angles. You want to emit only at 4.26 micrometers. There was a mistake here. You see it was 4.5, but not too bad. That was the first generation of samples. So we want to emit locally here, and we want the emissivity to be blue, 0 in all the rest. How can we design this? The idea is the same basic idea. In this case, the losses take place in the platinum, not in the silica in this case. And here we have a transparent dielectric resonator. The field is enhanced here in this micropillar. And by controlling the distance between the micropillar, where the field is very large, and the platinum, so the tail of the field penetrates in the platinum, and you have Joule effect in the platinum. So by controlling the distance, you can adjust how much losses you have. Then to have 100% emissivity, you need to have equality between relative losses and ohmic losses. So these relative losses, how you manage to do that? Here we have a grating that would not emit anything if this radius would be equal. And by introducing a slight difference in the radius, we change the period of the grating. If they are equal, the period is, that's a cell of the grating. If they are not equal, the cell is twice bigger. So by doing that, we change also the Brillouin zone, and we change the coupling to the far field. So we break the symmetry of the system. In jargon, this is called the bound mode in the continuum. In practice, this means that you are introducing a grating which perturbs the systems and scatters light. You clearly see on the picture that indeed they are different. And it's by playing with this radius difference that you can control how much it scatters light. So this is a very nice device where by controlling some parameters of the metasurface, you can indeed control some properties of the emitters. So in that perspective, it's a beautiful design. By the way, this is the measurements. This is the theory assuming that silicon is transparent in the infrared. And this is the theory when we account for the fact that there are losses in silicon in infrared. We all learned that if the energy is smaller than the gap, there is no absorption. But actually, there are still some absorption due to phonons. So you need to take this into account. Otherwise, it doesn't fit. In the SEMA-NR project, we designed a different emitter, which is made of plasmonic resonance here. So we have gold patches here. And again, you see that we are able to manage a strong emissivity at a well-defined frequency. Here it was exactly 4.26 micrometers, and within a narrow angle that can be controlled. If you notice, the control is here given by the folding of the Brillouin zone. So the parameter of control is really the period of the grating here. So it's possible to design something where we control the emission angle and the resonance frequency. How we solve the issue of efficiency? Is it possible to have an incandescent source, a light bulb, which is efficient? In the visible, no. In the visible, you all know that the light bulbs are operated at 3000 kelvins to emit in the visible. 3000 Kelvin, you vaporize the metal. So you need to have gas to collect the vaporized metal and redeposit them. So it's a very complex chemical process to increase the lifetime of the light bulbs. If you go to infrared, you can just increase the temperature to 1200 degrees. That's enough. At 1200 degrees, you do not vaporize the metal. So you can operate the device in vacuum. If you operate in vacuum, there is no more convection losses. So you solve the main problem of energy losses. The remaining problem is that you have your membrane, which is hot. It has to be attached to something. So there will be conduction losses. So what you do is that you only hit in the center and you do not hit there. So that's what's happening. You hit in the medium, so there is a gradient of temperature. So you have a flux, conduction flux going there. And you have radiation losses on the surface. It's not convective losses because you are in vacuum. So you have radiation losses. Radiation losses, you are happy with that because that's what you want to do. Because of what I showed before, you are able to control the radiation losses to have only the relevant angle and direction. So that's exactly what you want, these radiation losses. You want to suppress conduction losses. So, well, that's exactly what you do. Since you are hitting only there, this, you still collect light and you see that it decays the temperature and you can manage to have a cold temperature here. So if you just make this thick enough and then you have a tiny piece to hold the sample, you can suppress conduction. So you can engineer convection and conduction and suppress that. So there is nothing fundamental that prevents you to isolate thermally the system, okay? So your efficiency is not fundamentally limited. It's a matter of engineering. Now, I turn to the modulation. Is it possible to modulate thermal emission very fast? So that's your signal. It's a product of the emissivity and the specific intensity, the radiance. So there are two strategies to modulate. Either you modulate the temperature or you keep it hot and you modulate the emissivity. So modulate emissivity would be that you find a way to have a material that is either a black paint, it emits a lot, or a mirror, it doesn't emit. So you need to find a material that turns into absorbing, non-absorbing material. This can be done, it's been done here in the group of Professor Noda in Japan, in Kyoto, by having a stack of 63 quantum wells. So these quantum wells absorb. To have a significant absorption, a single quantum well is absorbed like 2% or 1%. So to have a significant absorption, you need 63 quantum wells, which is quite expensive to do. You see that they managed to have 80% absorption. And by applying a voltage, you can remove the electrons from the quantum well. So now it cannot absorb anymore. And the time it takes to remove the electron is only limited by RC constant. So it can be very fast. They managed to demonstrate 600 kilohertz modulation. So it stays hot and it emits or doesn't emit, depending on the voltage that you apply to the system. This is a completely different system where the modulation is even more impressive. This is a piece of graphene. In that case, what you modulate is the temperature. You just apply the huge voltage, so you have a huge current flowing through graphene. There are losses, and the Joule effect increases the electronic temperature of the electrons, but these electrons are not in equilibrium with the phonons of the graphene. You can have thousands of kelvins. So when you have thousands of kelvins, you emit indivisible. And the signal is here, and you see the time. This is absolutely amazing. That's 1 nanosecond. So here the period of the modulation is 300 picoseconds. So how is it possible that it cools down? Once you stop hitting the electrons, they cool down by electron-phonon interaction. And the time it takes for electron-phonon interaction is 1-2 picoseconds. And the thermal heat capacity of the phonon is immensely larger than the heat capacity of the electrons. So the lattice doesn't heat match. So this is amazing, but the area is extremely small. It works in the visible, but using very good detectors, because since the area is so small, you have very few photons. And if you go to the infrared, then forget, you have nothing. The area is too small, and the sensitivity of the detectors in the infrared is very bad, so you will never get any signal. So to have a temperature modulation that could be fast, we introduced this concept, which is based on a metasurface composed of a periodic array of platinum wires. The idea here to modulate is to heat only the platinum wires by Joule effect. So we apply the voltage, we have current flowing in the metal. So the heating is only a heating of the metal. When you stop heating, the cooling is made either by convection, very low, radiation, very low, or conduction. That's by far the dominant process. So you keep this spacer here, which is made with silicon nitride, cold, and the cooling by conduction is very fast. Very fast, what does it mean, very fast? It's conduction. Conduction, the typical conduction time is the distance of where the heat have to diffuse. So this is h squared divided by thermal diffusivity. So it goes like the thickness square. If you make a thickness which is nanometers, then it's pretty fast. With 25 nanometers, you get something which is on the order of 25 nanoseconds, which is pretty fast. The same physics applied to the pipes that goes to your home. You don't want during winter, overnight, your pipe freezing. You make the same calculation. Instead of 25 nanometers, you take half a meter, and it works for the whole night. So it goes like the square. And there's between 1 meter and 10 nanometers, you have several orders of magnitude square. It does the job. So heat transfer is pretty fast at nanoscale. Now, problem is 25 nanometers is not a lot of metal, and we want to absorb everything to be able to emit everything. Remember Kirchhoff. So to enhance the absorption, we use a mirror here, and we design this spacer in such a way that an incident plane wave will be reflected and will produce an interference that has a maximum, an anti-node right here where we place the grid. We can optimize these things in order to have 100% absorption. So the choice of platinum is made because it can sustain high temperatures, because it does not delaminate on silicon nitride. And on top of that, for free, we have the fact that it's an excellent thermometer. So we can measure the resistance. We are, in any case, applying a voltage to this to heat. We can measure the resistance, and from that we can derive the temperature of the platinum. For the design, we use Kirchhoff law. But Kirchhoff law cannot be applied here, because Kirchhoff law is valid when you have a body at temperature T. And now I told you I'm heating the wires, but the substrate is cold. So I have a field of temperature. I don't have a temperature of the sample. So this is more complicated. So we generalize Kirchhoff law, and this can be done, I mean, using the arguments of Kirchhoff, of course you cannot. But using this vision of electrodynamics of thermal radiation, saying that thermal radiation is due to local currents, then because these currents are local, you can introduce a local loss under a local temperature. And we were able to prove this generalized form of the Kirchhoff law, so the total emitted power for a given body is the integral of the local absorption. So if your body has a total absorption cross-section, which is given by that. Of course, the total absorption in the body is the sum of what is absorbing this volume, this volume, this volume, this volume. This is what is written here. So this is the local absorption. And you can prove that if you multiply the local absorption by Planck's function at the local temperature, then it works. So we can generalize, this is a local form of Kirchhoff law. And with that, we can model the system with hot wires and cold samples. So of course, we need now to compute the local absorptions and design taking this into account, but this is doable. So we did the design, we fabricated the sample, we made some measurements, and this is the first example of fast modulation. We send pulses, which are pretty short, and we look at the signal. The signal is the noisy one, and you see that it's pretty short. Then we made a systematic measurement as a function of frequency. And we have different regimes, which corresponds to different temperature regimes. Here the decay goes like one. So this is the one that is of interest. You see that there are two different polarizations, and TE emits much more than TM. This is because we're using grid, and you may know that grids of metallic wires are using as polarizers, linear polarizers. So we are emitting linear polarization here. So that's another cross in the list. We're controlling the polarization of the emission. And here the decay goes like 1 over square root of omega. The strong interruption here is due to the cutoff of our detector, which was at 20 megahertz. So we were able to prove modulation up beyond 10 megahertz. That's the spectrum. That's an interesting question, the spectrum. I'm just told you that we're modulating because we're modulating temperature, and keep in mind, the spectrum is black body spectrum, which depends on temperature. So the temperature is changing all the time, the spectrum is changing all the time. So there is no such a thing as the spectrum of the system. However, if you put a detector, a lock-in, and you make the measurement at a given frequency, then you can define the spectrum at that frequency. In time, it changes all the time. But in frequency domain, you can define the spectrum. And we can show that it's proportional to the temperature derivative of the Planck's function. So our spectrum is no longer proportional to Planck's function, but to its temperature derivative. So here again, you see the experiments and the theory with good agreement. And finally, we wanted to control polarization, and we wanted to do something more challenging, which is to emit circular polarization. So I just told you that with a linear grid, we had linear polarization. So we introduced in the system chiral elements. And the simplest way of doing chiral elements was to introduce these zigzag structures. So this is the sample which was fabricated. Actually, this is the only sample that was fabricated because this was during COVID time. So luckily, the first sample worked. It was not perfect, but this is what we have. Those are calculations. So the design, of course, this is hours of numerical simulations before fabricating to make sure that there will be some effect. So all the parameters here were optimized, and this is the result. So the quantity that we use to optimize is to compare the absorption in the metal, Kirchhoff law, keep in mind, we emit if we absorb. So we wanted to enhance the absorption in right circular polarization and reduce the absorption in left circular polarization to make sure that we have a huge contrast. So this is a picture of the local absorption rate in these metallic structures. And you see that indeed, where we have introduced this zigzag, this chiral element, this is where we have a significant difference in absorption as expected. We even computed the quasi-normal modes for the specialist of those things to understand what's going on. And indeed, we can identify a few electromagnetic modes of that structure which are responsible for this behavior. Those are the stocks elements. We are plotting here the total intensity. The stocks element of interest is the difference between these two, and it's plotted here. And you see that we have 40% degree of polarization. Okay, with that, I came to the end of what I wanted to show you regarding thermal luminescence. I'll take 2 more minutes to briefly give some ideas regarding what I said, photoluminescence. The first thing I want to show is this very basic figure where we have valence band and conduction band for a semiconductor. And the point I want to make here is that there is no fundamental difference between thermal emission, electroluminescence, and photoluminescence. In terms of emission of light, all of them are electron-hole recombination. So that's exactly the same mechanism. The difference is how do you excite an electron in the valence band to get this electron into the conduction band. And either by heating, and you have a high temperature distribution, or by sending a photon or applying a voltage. So the difference is really how you excite. In the emission process, they are one and the same. And because of that, everything I told you before can be applied to photoluminescence and electroluminescence. I skip all the details. In the numerical modeling, we need to introduce some photon chemical potential. This is an interesting set of measurements done by Aloïs de Giron, where there are different electroluminescence and photoluminescence curves with different spectra. He was very puzzled to have the same sample with so many different spectra. And it turns out that we could explain the differences by just fitting all those data and assuming that the local temperatures were different and the local cavitation potentials were different. And indeed, all the spectra fit when you fit them by this function. So this is a clear indication that yes, all these electroluminescence, photoluminescence are described by Kirchhoff law. That's what I'm saying. And you can use Kirchhoff law to analyze quantitatively all photoluminescence and all electroluminescence experiments. That's the key message. Kirchhoff law can be used to model photo and electroluminescence of any metasurface. And in particular, it enables you to account for strange spectra. And the final thing I want to show you is this. This is a metasurface, so again, an array on silver. And we have deposited on top a layer of nanoplatelets. They are kind of quantum dots. And you see that this is what we design as emission spectra. So we were able to convert the emission of these guys into something directional. This is the samples. They are real, they are fabricated. And so that's the final result. You see that with a layer without grating, that's the emission. That's what you would expect. You have full layers of emitters. It's isotropic. And when you deposit on this grating, that's what you get. So it is possible to control the directivity of emission of these spontaneous emissions things. So we've been able to indeed, although all of these emitters are incoherent, make them coherent. This is because the emission is mediated by the plasmon, and the plasmon has relative losses which are directional. That's the trick. With that, I'll stop and I thank you for your attention.